Our next speaker is Basanbat Sagan. He will be talking about the crustal thickness and VPVS ratio in Mongolia.
Hello, everyone. So I'm from Mongolia. So my name is Basanbat Sagan, and I work as a research scientist at the Institute of Astronomy of Geophysics. So today I would like to talk about the research on the crustal thickness in beneath Mongolian territory. So we currently use the very simple 1.5 space seismic velocity model in Mongolia for seismological research and earthquake processing in Mongolia. So for Western Mongolia, so we use very, sorry. So for Western Mongolia, we use very simple model consisting crustal thickness of 45 kilometers. So in contrast for Eastern Mongolia, so we use a model with crustal thickness of 35 kilometers. So however, using global reference seismic models are not suitable because of the differences in crustal thickness and the seismic velocity. So we also use seismic velocity ratio like 1.73 in the seismological research in Mongolia, which derived in 1975 from photograph of the 1970 Tsagan earthquake. So in the recent years, number and the density of the permanent broadband seismic stations in Mongolia have increased significantly. So for this reason, it's now time to renew the crustal thickness values used in seismological studies in Mongolia. So our goals are like to determine the average thickness of the crustal thickness beneath broadband seismic stations in Mongolia, also to determine the seismic velocity ratio, Poisson ratio in the crust, and also final goal of our study is like to make a general map of the crustal thickness beneath Mongolian territory. So in this slide, so you see the periodic studies which done by Russian scientists in Mongolia. So in the early 1960s, Russian scientists studied crustal thickness and Mohorovich discontinuity beneath Mongolia using gravity data. So according to the results, crustal thickness beneath Mongolia thickens from east to west, reaching like 40 to 55 kilometers. So based on this gravity research study, Hilko and Balchinum, they later created map of the Mohorovich discontinuity beneath Mongolia. So in this slide, you see the four major seismological surveys which was conducted in Mongolia. So please refer to this slide for the titles and the timeline of these projects. So it's part of these projects, so more than 200 mobile seismic stations deployed across Mongolia. So distribution of station covers like Gobi Altai region, Mongol Altai region, Hangado mountain, and Khupskul area, as well as southeastern part of the country. So using data from these projects, so those researchers done study the crustal thickness and the seismic velocity structure beneath this mobile station. So these seismological studies in Mongolia utilize the teleseismic receiver function method. So the main output from these studies was like a crustal thickness estimation beneath these mobile stations. So by combining these results, so we can create a crustal thickness map as shown here. So, however, crustal thickness hasn't been determined in the western and eastern and southeastern part of the Mongolia. So based on this previous study results, so we assume that like crustal is thicker beneath seismic stations in the western Mongolia. So also thinner must be thinner in beneath stations in the eastern region. So also we also assume that crust beneath in central Mongolia is approximately like 45 kilometers thick, which is consistent with other research which was done in Mongolia. So in our study, we use the teleseismic receiver function method, which is one of the primary seismological technique for determining the crustal thickness. So basically, receiver functions are like a time series computed from three component teleseismic seismograms. So they reveal like a relative response of the Earth structure beneath the seismic station. So for inversion of the observed receiver function, we applied Ch2 stacking algorithm to Ch2 stacking algorithm, and we determined the crustal thickness and VPVS ratio as well as like a Poisson ratio. So this Ch2 method uses like a delay time of the direct P wave, also the Moho converted PA path, and also other associated crustal multiples. So in this slide, you see the station distribution of Mongolia. So also, for this study, we compiled a comprehensive database using data from both mobile and permanent broadband seismic stations in Mongolia. So this figure shows the distribution of pre-selected teleseismic events used in our study. So also, you see the observed receiver functions for BU LM station is an example. So after that, we used these observed receiver functions for the Ch2 stacking inversion to estimate the crustal thickness as VPS ratio. So now we are reaching the study result. So let's talk about the study result. So using teleseismic receiver function and Ch2 stacking inversion, we determined the crustal thickness beneath the permanent seismic station in Mongolia. So according to our result, so Mongolian crust is thickening from east to west. So thick crust was found beneath HVDM station in the Mongol Altai range, or in the you see it in the right side. So with its thickness is like reaching 63 kilometers. So thinnest crust was measured beneath DABM station in eastern Mongolia is like 36 kilometers. So we say that we determined that the average crust thickness beneath central Mongolia like reaching 43 to 44 kilometers in central Mongolia. So there is one notable anomaly we identified in this study. So crustal thickness beneath BLM station is located in north central Mongolia, which it was determined like 37 kilometers, which is we say that this is anomaly. So in this slide, so we show the VPS ratio and the Poisson ratio determined by our study. So so next slide. So this is our study this is our main outcome of our study. So to construct a comprehensive map of the crustal thickness beneath Mongolian territory, so we integrated result from previous seismological surveys with the result of our study. So figure A shows the crustal thickness from previous seismological studies, and figure B shows presents results from our study. And however, when combining these two results, data sets, so some areas still remained without crustal thickness values. So to complete this, to address these remaining data gaps, so we incorporated the values from the crust 1.0 global crustal thickness reference model. So as a result, so we were able to produce like a general and complete map of the crustal thickness beneath Mongolia. So on this slide, you see our main result. So based on this map, so we say that the crust beneath Mongolia is thickening from east to west. So once again, the thinnest crust is still found in the eastern Mongolia. So while the thickest crust is located in the western region in Mongolia. So in summary, so crustal structure beneath Mongolia can be like categorized as follows. So thin crust we found in eastern Mongolia. So medium thick crust is in central Mongolia. Thick crust is in West Mongolia. So Now we are moving discussion section. So we observed very so amplitude and features of the Moho converted PS pulsar crustal multiples vary between stations. We observed that. So for example, so a strong PS pulsar seen on the BULM station and DZBM station. However, so we don't see a strong. We don't see strong. We see the very weak PS pulsar at the HBDM, which is located in Western Mongolia. So HBDM station. So according to the so HBDM station located in by tectonostratigraphic terrain map. So HBDM is located in accretionary wedge terrain, which is a geologically very complex. So BULM station sits on a like a Permian Triassic volcanic plutonic belt, and the DZBM station sits on a like a island arc terrain. So we say that we think that the complexity of the accretionary wedge terrain beneath the HBDM likely causes scattering and distortion of the Moho converted PS parts, so due to intense deformation and fault in this Mongol range. So in contrast, so we observe more stable in contrast, so we observe, we say that under BULM station and DZBM station, we say that beneath these two stations, we see like a sharp Moho, something. So it says it is suggesting like a more homogeneous crustal structure beneath those stations. So second discussion point is anomaly beneath BULM station. So we observed relatively thinner crust beneath this station. So to investigate this anomaly, so we installed the additional broadband seismic station near this station. So study results shows that the receiver function observed at these two stations are nearly identical. So determined crustal thickness, VPS velocity Russia and Poisson Russia are very close. So therefore we say there's hope. Therefore we trust our results. So we observed relatively thinner crust beneath this station. So this is the second discussion point. So final discussion point is a comparison between the crustal thickness map from seismological studies and other geophysical methods. So on this slide, so we compared the overall crustal thickness beneath Mongolia with the result of the gravity field studies. So we observed that zones of very high negative Bouguer anomalies corresponds to regions of the crustal thickening, and areas with a relatively small negative anomalies align with thinner crust. So this clear similarity between these two maps suggests as like a meaningful correlation. So we believe that integrating multiple geophysical method with a seismological study will greatly improve our understanding of Mongolia's crustal structure. So now we are reaching the conclusion. So I will not read this all sentences. So finally, we saying that our result is contributing to global seismological studies. Thank you very much for your attention.
Thank you. We don't have much, maybe just for a short question, one.
I have one. Your gravity data, was that satellite gravity, or did you have ground-based campaigns?
Say again, what's that?
The gravity data, is that from the satellite, or did you conduct ground-based gravity campaigns? Okay.
Oh, it's on now. Sorry, beg your pardon. Thank you for the talk. This is really a comment rather than a question, that more recently there's been an acquisition of quite a lot of magnetotelluric data across Mongolia, particularly in the central part. And you can often identify the MOHO as a resistivity jump. And it would be interesting to compare also alongside the gravity with the magnetotelluric results, I think.
Okay, got it, thank you.
Okay, if no more question, thank you again.